Hey students, in this video we're going to talk about double integrals in polar coordinates. So in this section we're going to be integrating over what we call polar rectangles, and it's just a region formed by two curves. There's going to be an angle that the region starts at and an angle that that region ends, and those are going to be our R limits for integration. Um, we have these four common formulas we use for polar coordinates. We should already know that x is r cosine theta, that y is r sine theta, that x squared plus y squared is equal to r squared, and that tangent theta is y over x. So with those conversions, if we're integrating a function, we're going to say z is equal to like f of r theta. And then again, the r and the theta are going to come from when we make the substitutions of x and y being a function of r and theta. Um, it turns out that we get this nice integral that is the integral of the function times r d theta. And this is key. Don't forget the r after the function, because it makes sometimes it makes the problem go from solvable to unsolvable if you don't include the r. So most of this is pretty straightforward. Sometimes we'll have to find our angle limits by using a projection down on the xy plane. I think that happens in the second example. So for this first one, it's pretty straightforward. It's a paraboloid that's bounded by the xy plane. If we want to see what that looks like, it's 9 minus x squared minus y squared. So it's just this paraboloid here. And if we project this down to the xy plane, because that's the region that we're integrating over. So when we're integrating over this region, and again, the region is the intersection of the two surfaces. The other surface that we have is z equals 0. And that's just the xy plane. So what we're always integrating over is the region of intersection. That's where our volume is bounded. So now it's going to be clear that it's a circle of radius 3, and so our limits are from 0 to 3, and then from 0 to 2 pi. So our outer interval, ugly color. So our outer limits are from 0 to 2 pi. Our inner limits are from 0 to 3. And 9 minus x squared minus y squared is really 9 minus x squared plus y squared as a quantity, which is 9 minus r squared. And again, we're using the conversion that x squared plus y squared equals r squared. So here, what we're really integrating is 9 minus r squared r dr d theta. So that inner integral, if we distribute our r, we have 9r minus r cubed dr, which turns out to be 9r squared over 2 minus r to the fourth over 4. And we're integrating from 0 to 3. So when we substitute in 3, we're going to get 81 over 2 minus 81 over 4, which is just 81 over 4. And so our outer integral is from 0 to 2 pi of just 81 over 4 d theta, which is going to be, nope, we don't need the integral anymore. This is going to be 81 theta, 81 over 4 theta, evaluated from 0 to 2 pi. So that's going to be 162 pi over 4 minus 0 pi over 4. So that equals 81 pi over 2. So the volume of that region is 81 pi over 2. That's a pretty straightforward example. Here's one that is not so straightforward. So there are a couple of ways to do this one and come up with a similar result, we're going to take the easiest path. So let's look at, if I remember this, it was 8 is 8 minus x squared minus 3y squared. All right, so we can see this is a nice elliptical region. And then we also have, it was x squared minus y squared. So this is a hyperboloid. Um, let's change this color to maybe green. Yeah, that'll work. So now what's different is, let's turn this off for a moment. So look at the projection down in the XY plane. The region that we have that's above, so it's bounded above by this curve and below by that curve. We want that overlap region, like right, it's tough to see, but it's contained like here, like this inner part. Let's screenshot this. Make sure I'm looking at that correctly. Yeah, so let's screenshot this. So the region that we're integrating over is like right here. And because of symmetry, we end up with the same portion like over here. So if we integrate it in one direction and just double it, we get the volume. We don't have to worry about two separate intervals. But this is not going to be an integral that we're just going from 0 to 2 pi over. So again, so now the question is, how do we find our limits for integration? Well, so the first thing is we have to find our R limits. So now like we're integrating over the region where they intersect. So that's going to be when 8 minus x squared minus 3y squared is equal to x squared minus y squared. And pretty quickly we'll get 8 equals 2x squared plus 2y squared. So 4 is equal to x squared plus y squared, which also equals r squared. So we end up with 4 equals r squared. So our radius is 2. So we're integrating from 0 to 2. So we know our r limits are from 0 to 2. And in particular, r is 2. R is 2. So now the other thing is, now it's important to understand that we're integrating over a region that's projected down. It can be projected down to the XY plane. And so that's going to occur when z equals 0. So there are two ways to do this. We'll do it the easier way. If z is 0, then we can set this equation equal to 0. So 0 is going to equal x squared minus y squared. So y squared equals x squared. And so now we can like take the square root of both sides. So y is going to equal plus and minus x. So remember that y is r sine theta. In this case, r is 2. So we have 2 sine theta equals plus and minus 2 cosine theta. And we could divide both sides by, we'll say the 2 cosine theta. So plus and minus sine theta over cosine theta is equal to 1. Well, that's tangent theta equals 1 and tangent theta equals negative 1. Those are the two equations that we're solving. So tangent theta equals 1 implies theta equals positive pi over 4. And then tangent theta equals negative 1 implies theta equals negative pi over 4. So those are our limits for integration for our angle. Now again, if we look at this diagram, that actually makes sense. We'll turn off the so if we look at the darker region, that looks like a 45-degree angle. And if we look at the angle that's in quadrant 4, that looks like a negative 45-degree angle. So those limits actually do make sense. So our integral is going to be from negative pi over 4 to positive pi over 4. But remember, we said we're going to double the result at the end. So it's going to be like 2 times this. And again, the reason that we double is that we have another region over in quadrants 2 and 3 that we have to worry about. So 2 times the integral from negative pi over 4 to pi over 4, and then r was from 0 to 2, and we want the upper function minus the lower function. So this function is on top, the 8 minus x squared minus 3y squared on that interval. So we're going to have, if we take this function and subtract, we'll get, we can work it up here so we don't run out of room. So all we're doing is moving this function to this side. So that's going to give us 8 minus 2x squared minus 2y squared equals 0. So that's really just 8 minus 2r squared. So we have 8 minus 2r squared r dr d theta. Now, instead of taking a whole other step to distribute the r, we're just going to make that 8r minus 2r cubed. So we get 8r minus 2r cubed dr d theta. And so when we integrate the inner integral, we get 4r squared minus 1/2 r to the 4th, evaluated from 0 to 2. Now, fortunately, when we substitute in 0, we get nothing. We substitute in 2, we're going to get 16 minus 8. So 16 minus 8 is equal to 8. And so now we have this integral from negative pi over 4 to pi over 4 of just 8 d theta, and that's going to be 8 theta evaluated from negative pi over 4 to pi over 4, which is going to be 8 pi over 4 minus negative 8 pi over 4, which is really 16 pi over 4, which is 16 pi over 4, which is equal to 4 pi. Where is 2 pi minus negative 2 pi? How do you want to think about it? So our answer here is 4 pi. But remember, we have to double this at the end. So it's like 2 times this times 2. So the actual answer is 8 pi. Cool. That example is the same as the other ones. We set them equal. R is 0 to, 18. So R is going to be 3. Theta is 0 to 2 pi. Same thing for that one. So here. All right, so a quick review of some other stuff for polar coordinates. So generally the function isn't the problem, it's the region and finding the limits for integration that we want to concern ourselves with. Let's hop over to Desmos this time. And so Desmos, we're going to put this in polar coordinates. And we are finding the region that is r equals 2 and r equals 4 sine theta. So r equals 2 and r equals, I forgot, but I think it was 4 sine theta. 4 sine, do we have a theta symbol? Can I type in theta? Theta. Yeah, give me theta. All right. So what we want is to write a function that I think the instructions said outside of the red circle, but inside the blue circle. Now, obviously, with the visual, this is pretty easy to understand. Let's screenshot this as well. So what we want is the region that is, Drew, sorry about the blue, my bad. We want this region here. We want that part. So now clearly they intersect at pi over 6 and 5 pi over 6, and r is going to start at 1/2. I'm sorry, at 2, and go up to the outer curve, which is two. It varies based on where you are. So it's going to be from 2 to 4 sine theta. So when we're writing our integral, we would have, so R ranges from 2, the smaller circle, to 4 sine theta. And then our theta is from pi over 6 to 5 pi over 6. Now the theta you can always find. And that's just when the two regions equal each other. So that's going to be when 2 equals 4 sine theta, or 1/2 is equal to sine theta. And we should know that here theta is sine inverse of a half. And on the interval 0 to 2 pi, that's going to happen at pi over 6 and 5 pi over 6. But they're not unique values. We could have done this from, if we added 2 pi, so that would be what, 17 pi over 6. I'm sorry, 13 pi over 6 to 17 pi over 6. Any two angles that are consecutive would work. But on the interval 0 to 2 pi, these would work. So our integral would be from pi over 6 to 5 pi over 6, and then from 2 to 4 sine theta, and then we'd have some function, we don't know what it is, so we'll call it f of r theta, r dr d theta. So again, the function itself doesn't matter if the region is independent of the two functions. The reason we were setting these functions equal to each other in the other examples is that they imply a common region, and we have to like find the boundaries by setting them equal to each other. But if you're just given the boundaries, the function is agnostic of what we're doing here, so it doesn't really matter. Is there anything else? Nah. Example 6 is the same thing. You can try it yourself. It basically works the same. And this is a problem that we'll tackle in class. All right. So that's integrals over polar coordinates. Some of it will get more advanced, but we'll do the advanced stuff in class. Thanks for watching.